Hello everyone. So in this chapter, there are no derivations as per the syllabus because we have to study most of the concept qualitatively. So you have to understand all concepts, all important formulas, and I'll try to cover all possible questions that can be asked in your board exams. Right? So let us see the syllabus first, and then we'll study each and every concept. So first we'll study bar magnets and how a solenoid behaves like a bar magnet. Then we'll see how we can find the magnetic field at a point on the axis of a bar magnet and at the point on the equatorial plane. Then if we place a magnet in external magnetic field, then what is the torque experienced by the bar magnet? And then the properties of magnetic field lines and how we can categorize material as paramagnetic, diamagnetic, and ferromagnetic. Then we'll also see some of the example of different types of materials. And then we'll study the intensity of magnetization and magnetic intensity. Then what is the effect of temperature on the magnetic properties of different substances? So first, let us see what is a bar magnet. So a bar magnet is a permanent magnet which is made up of a ferromagnetic material. So you have to remember this. And how a solenoid behaves like a bar magnet. So if you look at the field line, so this is a bar magnet where the field line, they're coming out of the magnet from the north pole and they are entering the south pole. So we can say in a bar magnet, the field lines are from north to south outside the bar magnet, and it is from south to north inside the bar magnet. And if you look at the field line pattern in case of a current carrying solenoid, the pattern is quite similar as the pattern of field line in bar magnet. So we can say a solenoid behaves like a bar magnet. So now let us see how we can find magnetic field at a point on the axis of the dipole and at a point on the equatorial plane of the magnetic dipole. So here we are going to use analogy between electrostatics and magnetism. So first we'll see what is the formula for electric field at the point on the axis due to an electric dipole. And by using that formula, we can find the formula for magnetic field at that particular point by magnetic dipole. Now let us see. So in case of a at a point on axis, so in case of a electric dipole, this is positive and this is negative charge. And if I want to find the field at this particular point P, now this field for a general case, this field will be 2 kp r upon r square minus l square whole square, right? Where r is the distance of point P from the center of the dipole and where 2l is the distance between the two charges. And the electric dipole moment is 2l times q, right? Now if I use the this formula to derive formula for magnetic field, so basically we want to find the magnetic field by a bar magnet. This is north pole, this is south pole. And at this particular point P, the magnetic field will be in the right direction, in the direction of magnetic dipole moment. So in case of a bar magnet, the magnetic dipole moment is from south to north. So this is magnetic dipole moment. Now here, what you have to do, you have to replace epsilon naught with 1 by mu naught, and you have to replace the electric dipole moment with magnetic dipole moment. So I can also write this formula as 2 upon 4 pi epsilon naught P r upon r square minus l square whole square, right? So we can say magnetic field will be 2, instead of P we'll write m, r upon 4 pi, instead of epsilon naught we'll write 1 by mu naught. So 1 by mu naught times r square minus l square whole square, and this can be written as 2 times mu naught m r upon 4 pi r square minus l square whole square. Now this is for this is a general case. Suppose if r is very large in comparison to l, so this is r, right? And let us say the length of this bar magnet is 2l. So if r is very large in comparison to l, then we can write r square minus l square nearly equals to r square. So magnetic field formula will become 2 times mu naught mr upon 4 pi r raised to power 4, and this can be written as 2 mu naught m upon 4 pi r cube. Now this is the formula for short bar magnets. Short bar magnets is a magnet in which the length of the magnet is very small in comparison to the r, where r is the distance at which we want to find the field. Now this is the case of magnetic field at a point on the axis. Now let us see the case when where we have to find the magnetic field at a point on the equatorial plane. So for equatorial plane, let us first see the formula for electric field. So this is plus q, this is minus q. At this particular point, the electric field is in the downward direction opposite to the electric dipole moment, and this field is given as Kp upon r square minus L square, sorry, plus L square raised to power 2, right? Sorry, not 2 raised to power. Let me rewrite this. So in this case, we have, yes, so it will be raised to power 3 by 2. So that is the formula, general formula. And so I can write this as 1 upon 4 pi epsilon naught P upon r square plus L square raised to power 3 by 2. Now what you have to do, if we want to derive the formula for magnetic field, this is our bar magnet. North pole is upward, south pole is downward. And we want to find the magnetic field at this location. It will be opposite to magnetic dipole moment. So magnetic dipole moment is from south to north. So here the magnetic field will be north to south in the downward direction. And this B can be written as 1 upon 4 pi 1 by mu naught. So I have replaced epsilon naught with 1 by mu naught and electric dipole moment with magnetic dipole moment. R square plus L square raised to power 3 by 2. So this is mu naught times m upon 4 pi r square plus L square raised to power 3 by 2. Now if r is very large in comparison to L, then r square plus L square can be written as r square. So magnetic field will become mu naught m upon 4 pi r cube. So you have to remember both the formulas. This formula, this is the assumption based formula, and this formula is general formula, right? And here you have to remember this formula and this formula, right? So I hope you know how to find the magnetic field at a point P, point P on the axis and a point P on the equatorial plane. Now let us see the concept of torque experienced by a magnetic dipole placed in magnetic field. So again, I'm going to use the analogy. So in electrostatics, what we have seen, the torque experienced by electric dipole was P crossing. Now what you have to do, you have to replace P with magnetic dipole and E with magnetic field. So the torque formula will become M cross B, and its magnitude will be MB sine theta, where theta is the angle between the magnetic dipole moment and the magnetic field. So this is M and this is B and this angle is theta, right? So we can use this formula to find the torque. And this torque will be such that it will try to align magnetic dipole moment in the direction of magnetic field. So in this case, the direction of the torque will be out of the plane, right? Out of the plane. So, and we should also remember some important configurations of magnetic dipole in external magnetic field. If M and B are parallel to each other, we'll call this configuration as stable configuration. So they are in stable equilibrium because there is no torque experienced by the magnetic dipole and there will be no magnetic force. Then net force on the magnetic dipole will be 0 and the torque is also 0. We'll call this a stable equilibrium configuration. And if magnetic dipole moment and magnetic field are anti-parallel to each other, we'll call this as unstable equilibrium. Again, in this configuration, there is net force is 0 and the net torque is 0. I hope it is clear. Right now, let us see a question which can be asked from this concept. A small compass needle of magnetic moment M and moment of inertia I is free to oscillate in magnetic field B. It is slightly disturbed from its equilibrium position and then released. show that it executes simple harmonic motion, hence write the expression for its time period. Okay, let me draw the diagram. So let us say the magnetic field is in this direction, right? And earlier there was a magnetic dipole which was pointing in the direction of magnetic field. Now what we have done, we have slightly rotated or deflected this dipole by a small angle, theta. Theta is very small. So due to this, so now there is an angle between magnetic dipole moment and magnetic field, and we know that the torque experienced by the magnetic dipole will be given by m cross b, right? M cross b, and this can be written as mb sine theta in terms of magnitude. Now we have rotated dipole in anti-clockwise direction, but the torque is acting in the clockwise direction. So we can write this as torque is equals to minus mb theta, because theta and torque have opposite directions. And I have written sine theta is theta because theta is very small. So we can write sine theta nearly equals to theta. And we have studied that if a rigid body rotating about a fixed axis, then the torque is given by I alpha. So I can write torque as moment of inertia times alpha. So minus mb theta. So from here, alpha comes out to be minus mb upon I theta. So alpha comes out to be proportional to the displacement, angular displacement from the mean position. So this is the equation of simple harmonic, angular simple harmonic motion, angular SHM, where mb upon I is nothing but the square of angular frequency. So omega square will be mb upon I. So omega will be root of mb by I. And we know that the time period of oscillation is 2 pi by omega. So this will be 2 pi times root of I upon mb. So that is the formula that you have to remember. And this derivation is also important, right? So it can be asked in your exam. Now let us see the next concept where we'll study the different properties of magnetic field lines. So first property is magnetic field lines are continuous loop. What does it mean? They form a closed loop, right? And why they forms a closed loop? Because the magnetic flux through any closed surface is always zero by Gauss law for magnetism. So if I draw any closed surface, so whatever field line which is entering this closed surface should also leave the closed surface. And you can also remember that in magnetism, there are no monopoles, only dipole exist. Now let us see the second option. The magnetic field lines never intersect each other. What does it mean? So let us say there are two magnetic field lines. Let us take a hypothetical case. Two magnetic field lines are intersecting at point P. You should remember that if I draw a tangent to magnetic field line, it gives us the direction of net magnetic field at that location. So at the point of intersection of these two magnetic field line, there are two possible directions. One is along this tangent, another is along this tangent. So this is giving us two different directions for the magnetic field. And we know that at a particular point for a vector quantity, it must be having some fixed direction. So it is not possible. So that's why magnetic field lines never intersect at a point. The number density of field line in region gives the intensity of magnetic field. So what does it mean? If we have magnetic field lines which are quite close to each other, it means at this region the field is strong. But if we have magnetic field lines which are quite far apart, we can say at this region the magnetic field is weak. Now the fourth point, we have already discussed the tangent drawn to the magnetic field line at a point gives the direction of field at that point. So if this is the direction, if this is the magnetic field line, so if I draw a tangent at this particular point, then this is the direction of magnetic field. If I draw a tangent at this particular point, then this is the direction of magnetic field. Fifth point, a magnetic field line is directed from north pole to the south pole and outside the magnet, and from south pole to the north pole inside the magnet. This point we have already discussed when we were discussing the comparison between solenoid and the bar magnet and their field line pattern. Right. So now let us see a question. So why do magnetic lines of forces forms continuous closed loop? I have already explained. If I consider a closed surface, the net magnetic flux through that closed surface will be zero. So you can say integral B dot dA will be zero. And this is nothing but Gauss law for magnetism. And you can also write In magnetism, monopole does not exist. Does not exist. So that's why we have closed loop in magnetism. Now let us come to the magnetic properties. So first, let us understand the concept of intensity of magnetization. So intensity of magnetization. Now let us see what is intensity of magnetization. Let us say there is a material, and this material I have considered a small volume, say V. Now this is a small volume, and in this volume, the magnetic dipole moment, let us say, is in this direction, and let us say it is M. So we define magnetic intensity I is equals to magnetic dipole moment per unit volume. So that is the formula for magnetic intensity of magnetization. Now let us understand what is magnetic intensity. Let us take a case of a solenoid, and we can pass current through that solenoid so that we can have some magnetic field inside the core. And there is a magnetic core, right? So there is a material which get magnetized if you pass magnetic field through it. And we have studied the formula that magnetic field inside the solenoid will be mu naught times In, right? If there is no core, we can say the magnetic field will be mu naught times In. And do remember this factor In, which depends upon the external factor or the current in the solenoid, is known as magnetic intensity. So H is B naught by mu naught, right? So this is magnetic intensity. So when we have magnetic intensity, we can have intensity of magnetization in a material. Let us see. So inside the core, we have magnetic field by the current in the solenoid or due to the magnetization, right? So we can say magnetic field, net magnetic field inside will be magnetic field due to the current plus magnetic field due to the magnetization. And this B naught is nothing but mu naught times H, where H is the magnetic intensity. And this Bm, it depends. So this Bm, it is directly proportional to the intensity of magnetization. And the constant of proportionality here will be mu naught. And this intensity of magnetization is proportional to the magnetic intensity. And the constant proportionality here is chi times H. So this is a very important formula where chi is nothing but magnetic susceptibility. So magnetic susceptibility. And based on the value of chi, this symbol is known as chi, right? So that's why I'm saying it chi. So magnetic, based on magnetic susceptibility of the material, we can categorize materials in different types. So chi is magnetic intensity of magnetization divided by magnetic intensity. So do remember this. So if we plot, say on the y-axis, if we have magnetic intensity of magnetization, on the x we have magnetic intensity, then it will be a straight line and the slope. So if this angle is theta, so tan theta is nothing but magnetic susceptibility of the material. Right. And this magnetic susceptibility can be positive, it can be negative. We'll see, right? Okay, right. So now if I substitute I value in this equation, we will get Bm. So this will become mu naught times chi times H. So we can say the net magnetic field inside the material will be mu naught times 1 plus chi times H. And 1 plus chi is nothing but relative permeability of the core, right? So this is relative permeability of magnetic core. So we can also write B net as mu naught times mu r times H. And we can also write this as mu times H, where mu is the permeability of the core. B net will be mu times H. So mu is permeability of core. So I hope this concept of intensity of magnetization and magnetic intensity and magnetic susceptibility is clear to you. And do remember the formulas. Now let us see how we can categorize material based on the value of chi. So we can categorize material as diamagnetic, paramagnetic, and ferromagnetic. So in case of diamagnetic material, 1 plus chi, this value, or you can say chi value will be greater than -1 and less than 0. So we can say chi is negative. So 1 plus chi will be greater than 0 and less than 1. What does it mean? So if we have magnetic field, so that can be written as mu naught times 1 plus chi times h, right? Now this factor is less than 1, so it means the magnetic field inside the material will reduce. So here the field will reduce inside the core because of the core presence, right? Now in paramagnetic material, chi value is positive, it is greater than 0 and less than to some finite value, which will be very small number. So we can say 1 plus chi is greater than 1 and less than 1 plus epsilon. It is slightly greater. So 1 plus chi is slightly greater than 1. So we can say B will be mu naught 1 plus chi times h. So we can say B will be slightly greater due to presence of core. So in case of diamagnetic material, the field will reduce slightly, but in case of paramagnetic material, the field inside the core will increase slightly because of the core material. But in ferromagnetic material, chi is very large in comparison to 1. It is very large. So 1 plus chi is also very large in comparison to 1. So B will be very large in comparison to mu naught h. So in case of paramagnetic material, the magnetic field inside the core can be 2000, 3000 times stronger without the core, right? So B can be 2000, 3000 times more as without core, right? If there is no core, then we have certain field. If we have core, a ferromagnetic core, then the field will be 2000, 3000 times more stronger. Okay, let us see the example, the type of question that can be asked. So define magnetic susceptibility of the material. So we know that magnetic susceptibility is the ratio of intensity of magnetization and magnetic intensity, right? And you should just remember, and magnetic susceptibility is a dimensionless quantity because the unit of intensity of magnetization is same as the unit of intensity of also magnetic intensity, right? Right. So next, name two elements, one having positive susceptibility and the other having negative susceptibility. So we know that positive susceptibility in paramagnetic and ferromagnetic material, and negative susceptibility is in diamagnetic materials. So we'll see the example, right, in the later part of the video. And what does negative susceptibility signify? We'll also study this once we study diamagnetism. So permeability of a material is 0.9983. Name the type of the material it represents. I think they are talking about relative permeability, right? So relative permeability is 0.9983. So it means 1 plus chi is 0.9983. So we can say chi is less than 0. So chi is negative. So we have negative chi value for diamagnetic material. So this material will be diamagnetic. Now let's see one more question. So the following figure shows the variation of intensity of magnetization versus the applied magnetic field intensity H for the two magnetic material A and B. So identify the material A and B. So this angle is theta and this angle, that is theta 1, and this angle is theta 2. So we can clearly see that theta 2 is greater than theta 1. So we can say tan theta 2 is greater than tan theta 1. So we can say the chi value for second material or B material will be greater than the chi value for material 1. So we can say chi for B will be greater than chi value for A. So magnetic susceptibility of material 2 is greater than the magnetic susceptibility for material 1. So we can say A is paramagnetic and B is ferromagnetic. And we have positive slope, so that's why we have these two options, right? And suppose if there is a diamagnetic material, in that case the curve for I and H will be in the second quadrant. Let us there is a material C, so this is the angle theta. So here magnetic susceptibility will be negative. Now let us see what are diamagnetic materials. So just remember the examples of diamagnetic material which can be asked in your exam. So bismuth, copper, lead, silicon, water, sodium chloride, all these are the examples. And in these material, individual atom have no net magnetic dipole moment when there is no external field. So no external field present. So if there is no external field, then individual atoms have no magnetic dipole moment. So in atoms, what happens? The electrons are revolving around the nucleus. So there will be a orbital magnetic moment and also spin moment, right? So, but in diamagnetic material, overall the magnetic dipole moment of an atom is zero when there is no external magnetic field. And but if you introduce some external field, what would happen? The dipole, then the individual atoms will be having magnetic dipole, and these dipoles will align themselves opposite to the direction of the external field. So if external field magnetic intensity is in the right direction, the dipoles will be aligned in the left direction, and due to which the field inside the material has reduced slightly. So we can say when we introduce external field, there will be induced magnetic dipole in diamagnetic material which opposes the field. So let us see with the animation. So if we have a uniform magnetic field, and if I introduce a diamagnetic material in this field, what would happen? The field lines will come out. Can you see? The field lines have expelled out. So we can say weakly repelled by the magnetic field and move from the region of stronger field to a weaker field. And there will be a partial expulsion of external magnetic field. So some of the field lines has come out, so we can say partial expulsion. So do remember these properties of diamagnetic material and how the field inside the material decreases. So this is the phenomena. There will be an induced magnetic dipole moment which is opposite to the external field. Now let us see a very important phenomena which happens in diamagnetic material. So when we cool a diamagnetic material to a certain temperature, a very low temperature, right? For example, in mercury, that temperature is around 4 Kelvin. It exhibits infinite conductivity. It means nearly zero resistance, right? And this temperature is known as the critical temperature. And for mercury, this temperature is 4 Kelvin. Now let us see what happens. So there will be zero electrical resistance when when the temperature is below critical temperature. And if I show the field lines, then all the field lines will be completely expelled out from the material. So the field inside the material will be zero if the temperature is below critical temperature. So do remember this phenomena. And in this case, the material will also exhibit Meissner effect, in which the magnetic field lines are completely expelled out. So this phenomena is known as Meissner effect also. Okay, now let us see a question. So why are the field lines repelled when a diamagnetic material is placed in external uniform magnetic field? So when we place when place diamagnetic material in external magnetic field, then there will be an induced magnetic dipole moment which is opposite to the external magnetic intensity. So due to which the field inside the material reduces, and hence the field lines will expelled out. So you can remember this, right? How does a diamagnetic material behaves when it is cooled to a very low temperature? So when we cool diamagnetic material to a very low temperature, then we have a phenomena known as superconductivity, when there will be no resistance in that material and it will be having infinite conductivity. And in case of a mercury, that temperature is 4 Kelvin. So you can write this. And you can also draw this diagram when we have superconductivity situation, then the all magnetic field lines will be completely expelled out from the material and the field inside the material will be zero. Now the next type of material is paramagnetic material. Do remember the examples: aluminium, sodium, and then oxygen, copper chloride. All these are the example of paramagnetic material. And in paramagnetic material, unlike diamagnetic, individual atoms have net magnetic dipole moment, which is shown by this diagram, where different atoms have some magnetic dipole moment. But without external magnetic field, these dipoles are oriented randomly. So we can say for the entire material, there will be no net magnetic dipole moment. But if we introduce some external field, then these dipoles will try to align themselves in the direction of magnetic field, and then the magnetic field inside the material increases. So if I show you this with an animation, if we have a uniform magnetic field, if we place a paramagnetic material in this field, then the field lines will be expelled in, will come in, right? So and the field inside the material increases. So we can say individual atom have net magnetic dipole moment and no net magnetization if H is 0, and they are weakly attracted by the magnetic field, and they move from a region of weak field to a strong field, and there will be a partial inclusion of external magnetic field line. So do remember all these points. And now let us see what is Curie's law. It is very important law. It tells us how the magnetic intensity of magnetization varies with temperature. Here I am taking I, right? I is the intensity of magnetization. Intensity of magnetization for paramagnetic material. So it is inversely proportional to T, and this B is nothing but the applied magnetic field. So we can say I will be, C is the Curie constant, and B will be mu naught times H by T, right? So that this formula you can remember, where I will be inversely proportional to the temperature. So this is the graph for paramagnetic material with temperature. So it decreases with increase in temperature. This is I, right? And we know that I by H is magnetic susceptibility. So if I substitute this value in this equation, so I can write H times chi, which is C mu naught times H by T. So H will get cancelled out. Sorry, H will get cancelled out, and chi, or magnetic susceptibility, will be mu naught times C by T. So you can remember this formula as well. So this is the formula for paramagnetic material. Now let us see what are ferromagnetic materials. So these are the example: iron, cobalt, nickel, gadolinium, right? All these are ferromagnetic material. And what happens in ferromagnetic materials? In this we have domain structure. So these are individual domains, right? And in individual domains, the different atoms, they interact with one another and all are pointing in the same direction. So different domains have some net magnetic dipole moment, but all domains are pointing in the different direction. So we can say overall there is no net magnetic dipole moment. But if we have some external magnetic field, then all domains will tend to align in the same direction, and then we can say there will be an amalgamation of domains into a single giant domain, right? So here, can you see? So different atoms, they're aligning in the same direction, but if we have some external field, they tend to align in a particular direction, and then there will be amalgamation of the domains. So with the animation, I can show it. If we have a uniform magnetic field, if we introduce a ferromagnetic material, then the field lines will get expelled in, or they will come in, and the field inside the material increases. So we can say the strongly attracted by the magnetic field, they move from a region of weak magnetic field to a strong magnetic field, and they nearly complete inclusion of external magnetic field lines, because in case of ferromagnetic material, chi value is around 2000, 3000, right? And in case of paramagnet, it is around some positive number which is very small. And there exists domain structure that we have already discussed. So these are ferromagnetic material. Now let us see what are hard and soft ferromagnet. So hard ferromagnet, if magnetization persists after turning off external field. So when we turn off the current in the solenoid, then there will be some magnetization left in the core. So such materials are known as hard ferromagnets. For example, alnico, copper, lodestone, all these are the example of hard ferromagnets, and we use these materials to make permanent magnets. And there are soft ferromagnets. If magnetization removed after turning off the external field, we'll call them soft ferromagnet. And we use these materials to make electromagnets, because we want electromagnet to behave like a magnet once there is a current in the coil, and it should be completely demagnetized if there is no current in the coil. So the example for soft ferromagnet will be soft iron. And now let us see the Curie temperature. What is Curie temperature? So it is a temperature at which the ferromagnetic material, there is a transition from a ferromagnetic material to a paramagnetic material. So if we have a temperature greater than the Curie temperature, there is a transition from ferromagnetic to paramagnetic. So Tc is the Curie temperature, and the magnetic susceptibility for ferromagnetic material will be given by this formula, where C is the Curie constant upon T minus Tc, where T is the temperature at a particular instant. So do remember this formula. This formula we have already discussed when we were discussing paramagnetic material. So I hope this graph is clear to you. Now let us see the questions which can be asked. So draw magnetic field lines when a diamagnetic paramagnetic substance is placed in external magnetic field. So we have seen in diamagnetic case, there will be expulsion of magnetic field lines. And in case of a paramagnetic material, there will be inclusion of magnetic field line. Which magnetic property distinguishes this behavior of electric field line due to the two substances? So which property? Because they have different magnetic susceptibility, so that's why their behavior will be different in the external magnetic field. Right, so now let us see one more question. So why does a paramagnetic sample display greater magnetization when cooled? So we know that in case of a paramagnetic material, intensity of magnetization is given by C B by T, where B is the external magnetic field. So we can write this as C times, which will be mu naught times H, and this I by H is nothing but magnetic susceptibility of the material. So magnetic susceptibility will be C mu naught by T. So magnetic susceptibility is inversely proportional to the temperature. So as we decrease the temperature, magnetic susceptibility increases, and hence the paramagnetic material will show greater magnetization. So this is the explanation for this question. So here I conclude this video. So I have covered all possible concepts as per the syllabus. So see you in the next video, where I will cover electromagnetic induction. Thank you.